All right, well, let's get started. You all should be able to see the picture of Alexander Litvinenko in his hospital bed. Now you're all experts on him. What? I was not singing. You're making that up. You can't see him? Oh, yeah, you can't because I didn't push play yet. Now you can. You can't hear me. Brianna Banana. All right, looks like Brianna's on phone audio and not on. She needs to switch to computer audio. I know. Should I take attendance? Probably a good idea, isn't it? You know what I'm going to do? I'm a smart guy. Take it like that and figure it out later. All right. So, pick a step in the scientific method and explain how it could apply to the case of Alexander Litvinenko, who you should now be able to see on your screen. Now, you remember the case of this guy. So think about some observations that a person should or could or would have made, or some questions a person should or could have would have asked, or perhaps some background research that needed to be done on this case, or a hypothesis about what happened, who done it, those kinds of things, a way to test the hypothesis, etc., etc. So pick one of those out and write it down. And once you have, I will take a picture of what you've written down so that I know who is making an effort this morning. So how could that apply? Elizabeth Day, how would you test a hypothesis? All right, I want you to talk about how these things apply to the case itself. That's a good definition, Joshua. So you need to, I'll repeat myself, pick a step in the scientific method, one of these 8 steps, and explain how it would apply or could apply to the case of Alexander Litvinenko. It might be something we already talked about, but I want to make sure you guys are thinking about how the analogy of the scientific method works in the case of a murder mystery. So pick a step and explain how you would use that step in this case. Ready, go! All right, I see 4. Elizabeth, Shay, Harrison, and Guinevere. Yes, see if there's any other cases related to Litvinenkos. Nice job, Brianna. Sorry that was tough for you. question the people at the scene of the crime. Good. Like the scene where you think the crime took place. All right. Go ahead and put your response in there in the next 10 seconds so we can move on. 10, 9, 8, 7, 6, 5, 4, 3, 2, that all makes sense? You follow me there? Good. All right, good. I think you guys are thinking. I think you're using your brains this morning. How are your atom projects going? Are you guys having fun with that? Are you figuring that out? You working through it? You getting all the info related to your atom? Good. I'm glad you guys are having fun with it. Here's one little part of it. Who I like to hang out with? Helium. Nobody. I'm a noble gas. All right. Good. Good. Okay. The practical way. That's all right. Practical way is a good way. All right, well, today we're going to start thinking about how these atoms that we've been talking about combine to form molecules. In fact, see right here. How chemical reactions result from the making and breaking of bonds in a process that absorbs or releases energy. We're going to look at both of those things today. Those bonds are bonds between atoms forming things called molecules. Have you heard of molecules before? It is small. Here, this is bigger. You want it bigger? I'll make it bigger. Good. Good. So here's the part I was talking about before right there. But you can see other things as well, the types and strengths of the bonds, etc., etc. All of chemistry, the existence of the very subject of chemistry is just about how atoms bond with each other or how those bonds are broken and what happens when those things happen. That is all chemistry is. Crazy, huh? So we're now, as you can see, moving from atoms to molecules as a unit, and then we'll finish up with energy. But first, I'm going to ask you kind of an interesting question related again to the structure of the atom. Why is glass transparent? You see, if you hold up a glass, like a wine glass or a water glass or whatever, fairly thick, that light might have to pass through 50 million atoms or more. Even if it's very thin glass, it would be 50 million atoms just to get to your eye. How is it that light from, say, outside your window, bouncing off of your fence or the trees or whatever else is shining into your eyes, how could it pass through 50,000 atoms? Joel can't hear me. Well, lucky Joel. Not everyone is so lucky to not be able to hear me. You don't have a fence. That's good. Good for you. Well, Joel, part of the reason for that is that you might recall that these atoms, these 50 million atoms, well, all an atom is a large bit of empty space with a tiny little p in the middle. It would be about, if you blow it up, the P would be the middle of something the size of a football stadium. So those atoms, right, have tons of empty space. We've been over and over this a million times. You guys are sick of hearing me talk about that. But you'll never forget it, right? So, the better question might be, why is it that light doesn't just pass through everything? If atoms are mostly empty space with this tiny little nucleus in the middle, why is it that light doesn't just pass through everything? What do you think? Why does it not pass through my hand? Why can you no longer see my face? Why doesn't it pass through this tiny little thin little whatever this is? If all the atoms that make this thing up are mostly empty space, why isn't the light going through it? Oh yeah, Joel's sound is on phone audio too, isn't it? All right. Well, the answer, my fine feathered friends, has to do with the strangeness, again, of the atom. You see, it doesn't actually matter if the photon even hits the nucleus. The photon, in fact, I suppose you could say would go right through a nucleus anyway. What really causes photons to be absorbed or emitted is the way they interact with the electrons around the atom. You see, most of what's in a glass is simply silicon and oxygen, and atoms that form sort of a crystal structure like this. In fact, this is quartz, which is the purest form of silicon dioxide. And that's sort of the purest form of glass, but we put a lot of impurities into the glass. So it's, even though it's mostly silicon and oxygen, like sand, right? Did you guys know glass is made of sand, basically? Even though we put a lot of silicon and oxygen in sand to make glass. Yeah, that's right. We also put some impurities in to make it easier to work with, because quartz tends to just shatter more easily. It's not as malleable. It's harder. You have to get it really hot in order to melt it and shape it, whereas glass, when you have some impurities in it, you don't need to get it so hot. So glass would have a structure not so much like the one I just showed you, but a little bit more like this. Might be some sodium in there. It's not quite so even or so routine. It's a little more broken up. But still, it's mostly silicon and oxygen. And silicon and oxygen happen to not interact with light. Hardly at all. You see, what happens when light gets close to an atom is all that it does when it interacts with the atom is it causes an electron to jump to a higher energy state. And in that case, a photon is absorbed. But sometimes that electron can then jump back down to a lower energy state and emit an electron. It jumps back down to a lower state. It could jump down to this state, or it could jump all the way down to the inner state where it starts out in this animation. And so visible light is not strong enough. It's not, I should say, energetic enough to interact with the silicon or the oxygen to cause a photon to jump and an electron to jump and a photon to be absorbed. So the photon will pass through every single one of those atoms because it doesn't have sufficient energy to get that electron to absorb it. Kind of a strange answer, but I want you to understand that the nature of light, again at the atomic level, is very strange. And the nature of electrons is very strange. And all that light is, all light, any light that you see from anywhere, was emitted from an atom because an electron jumped from a higher energy state in that atom to a lower energy state in that atom. And that caused a photon of light to be emitted. In this particular animation, we're just seeing a photon being absorbed so that it then causes an electron to jump to a higher state. But that electron will eventually go back down to a lower state and emit a photon as it does so. All of the light around us is nothing but electrons jumping to lower energy states. Crazy, huh? Maybe, maybe not. Maybe it's not so crazy. That's one reason why more higher energy, like, you know, what is it, UVA, UVB, ultraviolet light? You guys ever put on sunscreen? That's exactly true, Shay, except for there are so many, atoms in any given substance that a lot of electrons can very easily jump down over time and keep emitting light. And they're constantly being energized, like on planet Earth, for example, because the sun is constantly showering us with light and photons that's energizing the particles around us, raising them to a higher energy state, and then they can go back down to a lower energy state to release a photon towards our eyes or something like that. So that's a good question, Shay. Have you guys ever put on sunscreen? I asked the question again because no one answered the question. All right, good. So the point of sunscreen is that it helps to reflect some of the light that would otherwise be absorbed by atoms in your skin, causing them to then burn, or to burn, causing your skin to get sunburned. When you're driving in a car, you might notice this, even if your arm, like this lady's arm you see is in the sunshine there. Now, I know none of you actually drive yet, do you? You poor things. Maybe some of you do, I don't know. But you see the sun is shining on this lady's arm through the window. And as it does so, it heats up her arm, but there are certain photons of light that cannot get through the glass. Even though visible light comes through, the ultraviolet light that gives you sunburn does not go through the glass. It's actually stopped because it's absorbed by those photons. And because it does that, you don't really get sunburned when you're driving in a car. That light will not burn you. Did you guys know that? That you can't get sunburned when you're driving in a car? If you have the windows rolled up, of course, blocked by the windows. Well, it's true. You can still get some bad, radiation that can cause cancer from the sun, but it's not the kind that's actually going to burn your skin. You have to be in the open air, otherwise the windows block that sunburn stuff from hitting you. Fun fact, science fun fact. All right, I'm going to skip this one. Am I going to skip this one? I want us to think now about how atoms join together to form molecules. So I'm simply going to ask you the question, what do you think the following images make you think of? What do the following images make you think of? And you could say anything. You don't have to say anything, scientific or whatever. Workers in the Matrix. Yeah, I like it. I like it. Oh yeah, pig snout. In ant farm, yeah, it looks like there's a bunch of ants or something in that picture, doesn't it? Well, these are actually representations. Oh yeah, it does kind of look like it could be space, huh? Like with something going on, I don't know. Well, both of these things represent molecules. Now, molecules you see come in all shapes and sizes, and molecules are simply more than one atom that are joined together. In this case, we just have a representation of what two oxygen atoms might look like when they're joined together. They're sort of overlapping a little bit. They're sharing electrons in their outer shells, which we're going to learn a lot about. Oh yeah, Star Wars. And that's a simple diatomic, it's just two atoms, but it makes a molecule. And they're both the same atoms, for example, oxygen. In fact, all of the oxygen you're breathing right now is not single oxygen atoms, but it's diatomic oxygen like this, where two oxygen atoms are joined together because they're in a much more stable state when they're like that. In fact, have you guys heard of ozone before? Ozone is simply oxygen when there are three oxygen atoms joined together. We call that ozone. If you added a third one in there, that would be something called ozone. It's much more common in the upper atmosphere than it is down here in the stratosphere. Or I mean the, what do we call this? The troposphere, where we live. It's much more common in the stratosphere. Now this other molecule, watch this. Okay. Oh, and you can actually see there's this. That's what it would look like if the electrons are kind of being shared. You can kind of see how that's represented there in those two oxygen atoms. But check this out. This is a large atom called myosin. Sorry, a large molecule, and it has thousands of atoms that make it up, and it gives it the structure that it can actually move junk inside of the cells of your body. Inside all of the about 40 trillion cells in your body right now, inside of each one, there are little proteins like this, which are moving junk around your cell on these microtubules that are kind of like ladders. And that's a molecule that is 20,000, has 20,000 components. In fact, let me look at my notes here. I can't remember exactly what it's made of. I don't even know how to look at my notes. Let me see if I can figure that out. Oh, there it is. Oh, kinesin on the right. Thousands of molecules. Oh yeah, it uses electrostatic attraction of its feet to drag junk to the edge of the cell and pitch it outside, as you can see there. So kinesin is the name of that particular molecule. Crazy. So I want you to remember that molecules are often small, but sometimes, especially in the human body, we create, and your cells create, enormous proteins that are thousands of atoms big. And they're just a single molecule all bonded together, but they are thousands of molecules. They're called macromolecules. All right. But in general, with smaller molecules like oxygen I just showed you, or H2O, water, which you can see right here, they always combine in simple fixed ratios. So just like we saw when we destroyed water, you guys remember this. There was a little bit more hydrogen gas than there was oxygen gas. So you can see here, this is kind of an animation of the electrons coming. They break up the hydrogen. The hydrogen goes out, and the oxygen then stays behind. That's right. And that's how the hydrogen gas was separated, and the other hydrogen would be separated as well. But you get twice as much hydrogen as oxygen because you have 4 hydrogens for every 2 oxygens, as you can see in the image here. And so rather than cookie dough, where you can simply add or subtract chocolate chips and it doesn't really matter that you have an exact ratio, atoms combine into molecules in simple fixed ratios. So for example, silicon dioxide, glass, or quartz, which we looked at before, is always 1 silicon atom, and then 2 oxygen atoms, and then those are connected to another silicon atom, and then 2 more oxygen atoms. And they form a lattice like that, but always in the same ratios. You're never going to have, like, it's always, in this case, going to be 2 to 1. It's never going to be 2.5 to 1, or, whatever. It always is going to be a fixed ratio. That's one of the rules of chemistry, which we learned just from studying it, seeing how it worked in the real world. It's called Dalton's law. It's the law of multiple proportions. And then you all remember reverse electrolysis. I think maybe I had this in the slideshow because I didn't go through it before, but people were getting ready to head to King George VI's coronation after, or George VI, because his brother stepped down because he was in love with some American hussy, and he didn't want to be king anymore. He'd rather just love her for the rest of his life. But unfortunately, when their boat tried to dock as it was coming from the UK, you might remember the Hindenburg blimp exploded and some people died. So they weren't able to see old George get coronated, sadly. And we sort of stopped putting hydrogen in blimps because that was reverse electrolysis. And of course, this is the image of a guy doing a little reverse electrolysis of his own, and you see what happens. If you have a balloon filled with hydrogen gas and you set it on fire, then it might continue setting on fire, creating a whole bunch of water. This is hydrogen gas in the presence of oxygen turning into water. Now, you don't see a bunch of water being created, but there is water vapor. That's what the flame is producing, is water vapor. So please do not try this at home. I wasn't able to show you that before. So lastly, molecules, when they combine or when they're broken apart, they always do it outside. You'd like to get second-degree burns outside. Well, that's a good idea. You can do whatever you want as long as your parents say it's okay, but I'm not going to do it because I don't want to go to the hospital. Molecules, when they combine or are broken apart, absorb or release heat. So you can see that when this is how H2O is broken apart into its constituent elements, right? How water is broken apart. Now, when water is being produced, like that guy with the balloon, right? He had a bunch of hydrogen molecules in the presence of oxygen. He gave a little spark to them to get them started, to get them going. So he had to start it on fire. But once it started, it produced enough energy to continue burning, right? As the two water molecules combine with oxygen to make H2O. That's what's on this side, is the water molecules. So as that water is being produced, does it seem like heat is being released, or does it seem like heat is being absorbed? What do you guys think? As that guy is holding that balloon, where those hydrogen molecules are combining with the oxygen molecules to make water, is heat being released or absorbed? I don't know if I have, Sam. I don't remember. That is correct. It is being released. The heat is being released. In fact, that's all that's going on there. And all of that heat, all of that flame is simply coming from the energy that's released when hydrogen molecules recombine with oxygen to produce water. That releases some small amount of energy for each molecule that's created, because this is a lower energy state for those to be in, and so some energy is released as heat. Oh, he makes water. Yeah, I don't think I've seen that yet. And so it's time now to remember, and you guys have already told me that the process on the right is the one that releases heat. This is the one that absorbs heat. In fact, you remember I needed a battery to break water apart, right? So I was putting heat or putting energy in from the battery to separate those water molecules into their constituent elements. But the reverse process actually releases that heat back out to the environment. So we have a word for those things. Endothermic is when heat goes into something, so that would be the one on this side. That's an endothermic chemical reaction because heat is going into the reaction. Exothermic is when heat is released, so that's what's on this side. This is an exothermic reaction over here on the right side, because as the hydrogen and oxygen combine to form water, they release heat. So exo, heat comes out of. So you want to remember exothermic is going to be dangerous. Those are dangerous reactions because heat comes out of them. Endothermic reactions, heat goes in. In fact, one endothermic reaction you might have used before is if you have a cold pack in a first aid kit. When you break that cold pack, it's not cold until you break it, And that starts the chemical reaction that actually pulls heat from the environment into the atoms themselves, but that makes it really cold because all that heat just goes into the bonds and it has to take heat from around it, from the substance that it's made of, to do that. Yeah, I guess it's like imports and exports. The thing that's hard to remember, though, is that it's not when things combine that heat is released. Sometimes when things are broken apart, heat is released. So sometimes these decomposition reactions would be exothermic. It's hard to predict sometimes whether a reaction is going to be endo or exothermic. It's just important to know how they work. All right, that's all I got for today, you all. Boy, do you only have to come to class for half an hour today? Lucky you. Oh my goodness. Can I find anything else for you? Nope, that's the end of the slideshow. That means you have all kinds of extra time to go and work on your atoms project. If you have any questions on that, please stick around and ask them to me. Otherwise, you are free to go. Thank you for being here today. Adios, amigos. Wait. Bye, Elizabeth. Tori, you want me to wait? You have a question? Are you in the middle of something? Almost done here.